So today we're going to do a different topic. It's still in shearing stress, but it's shearing stress in thin wall. Okay, we're going to look at shearing stress in thin wall. Now this will not be tested in your term test. Okay, term test 1. This will be tested in term test 2. Okay, so shearing stress in thin wall. Has two configurations. Okay, it has two configurations. So one of it is known as box beam, and the other one is known as wide flange. Okay, so box beam and wide flange, and I'm going to acquire the image on here. Okay, so what you see first, this is what we call a box beam, and then the next one is what we call a wide flange. Always does that to me. Okay, so you can see it's different. Okay, you can see it's different. Okay, so what is the difference between box beam and wide flange? Before we go on, let's look at the difference between a non-thick wall, a non-thin wall, and a thin wall analysis. Okay, let's identify the difference first. Okay, so I'm going to go on the side down here. Now all these images you will have. Okay, I'm going to go into non-thin wall. So non-thin wall is based on what we have done so far. Okay, non-thin wall. So I'm going to draw a structure that is non-thin wall. Go on. I think I'm going to today is not a good day for me. Okay, let's look at a non-thin wall. Okay, a non-thin wall. Let's say we have a non-thin wall. Okay, so a non-thin wall. Likewise, I'm going to draw it very similar. We have a box, for example. Okay, non-thin wall with a box. Okay, we have a box. Right. For a non-thin wall, right? Let's say we have identified where the centroid is. We have identified where the centroid is with the centroid. So this is our centroid. Okay, so this is our centroid. For a non-thin wall, right? This is the thickness. I'll draw the thickness. Okay, so this is the thickness of configuration. Okay, this is the thickness. And then at the centroid, you have to consider this thickness. Let me offset a bit, or let me just draw by hand. This is the thickness. All right, let's say you want to find the centroid. You use these two thickness over here, T1, and this is also your T1. Okay, that is for thin wall. I do apologize. I don't know why I'm feeling nervous for the first time, okay? It's so weird feeling, okay? So you should see me a bit shaky, okay? Right, so that is for non-tin wall, okay? Now let's look at tin wall, okay? For tin wall, the difference is this, okay? The difference is the thickness, okay? What is the difference? There are two things that are different, okay? So one is Q, what you see, those lines, those small pink arrows, they are your shear flow. Okay, so these are all your shear flow, all your Q. Okay, why I draw two? Because point A is known as our terminal. Okay, point E is also known as our terminal. Okay, so for box beam from a terminal, one shear flow go towards the left, the other shear flow go towards the what? Towards the right. Okay, so some of you might ask me, Eugene, what is this shear flow actually means? Like I mentioned before, it is equivalent to fluid flow. Yes, fluid flow. Now, can someone hear me properly, or because of the mask, you are having difficulty understanding me? Are you okay? Okay. So it's like fluid flow. So if you have a terminal at A, right, you put water in, water will go to the left, and water will go to the right. Okay. For thin wall structure, you have to think more this way. Okay. So the thickness now changes. Okay. What do I mean by thickness now changes? In the box beam, right, or in thin wall, the thickness is this is the thickness. Okay. So you can see in the flange region, so if I call this a flange, not French, okay, flange region. This is also the flange, right? It's different between the one for non-thin wall and thin wall. The thickness is different. So how to identify the thickness? Okay, so for thin wall, okay, for thin wall, the thickness, geometry, orientation, okay, is perpendicular to the shear flow Q. Okay, it's perpendicular to the shear flow Q. Now, there are similarities between thin wall and thick wall. Okay, can someone identify for me what are the similarities? So usually online now, I'll be sitting down there, come on, someone answer. Now I can see you. Okay. So obviously, I'm not coming. He's expecting us to answer. Can you all see what's the similarity? What did I say? Right? Is that the thickness is perpendicular to the shear flow. Right? Okay. Now, where is the part where it does not matter whether is it thick wall and thin wall? Anyone? At which region? Yes. Yeah. No, not at the terminal. At the, yeah, at the centroid where the wet is. Okay. Where the wet is, it does not matter whether you are thin wall or non-thin wall, because the thickness now, right? How do I define thickness? Is the geometry orientation is perpendicular to the what? To the shear flow. Yeah, right? So when that's the case, if we look at the centroid for the thin wall, the thickness is taken in this orientation. Right? You have to take both sides. Okay. Where else? And non-thin wall, the thickness is also what? P1. right? So now you see some similarities and some differences, okay? Later on, I'll give you a structure that will screw you up. What do I mean? I will include box beam, white flange, thin wall, thick wall, all into one structure. You should be able to identify when to use what, okay? Don't worry, I'll make sure you get that. Okay, now, let's say now, if we have an I-beam that is non-thin wall, again, okay, non-thin wall. Okay, non-thin, so we have an I-beam. Okay, non-I-beam. Okay, now, the next thing, oh, before I go on, can you all see the arrows in the shear flow in the thin wall analysis changes? Can you see that? Right, it changes. So what it means, okay, what it means is in thin wall and or the length of the length of the arrows, okay, determine the magnitude, okay, the magnitude of the shear flow. Okay, the longer those arrows means the higher the shear flow value. Okay, now let's look at the white flange. Okay, so on the right hand side is what we call white flange. Okay, so white flange, then we look at the non-thin wall. For the non-thin wall, right, if we look at the flange now, okay, as you can see, this is the thickness. Okay, this is our thickness. Okay, let's say if we want to find a point down here known as alpha. Okay, point alpha, that is the thickness that we will use. Okay, now if we were again draw on the centroid, all right, this is the centroid, then this will be our thickness. So now I think you can see some similarities also between thick wall and thin wall. Okay, now in thin wall analysis, okay, if you want to find at a point down here, okay, let's say now we change alpha to here, okay, the thickness you'll use is perpendicular to the shear flow. Okay, but before you do anything, you have to identify where the terminals are. Okay, so for the white flange, you have 1, 2. Okay, so we have terminal down here. You have another terminal here, and then over here and here, you have your terminus. Okay, so the inflow are coming from two separate terminal. The outflow is coming from two separate terminal on the outflow also. Now, the trick about point alpha is this. Okay, if you want to look at the stresses at point alpha, you only need to consider this area that I'm shading now. Okay, that's it. Okay, unlike if we want to consider point alpha over here, right, the area of consideration is this entire area. Okay, now I'll pick another point. Okay, I'll pick another point. Now let's say I want to find a point down here known as beta. Okay, which is the area do you pick? Anyone? Now the 5 rules still stand. I repeat again, remember the 5 rules I told you guys? Okay, it still works. Okay, so if you want to find alpha, okay, Do not be deceived by the direction of your what? Your shear flow. Do not be deceived by it. Okay. When I was teaching this class years back, I thought if it's coming from the top, right, everything has to move downwards. Yes, right? No. Okay. If we apply the 5 rules, okay, one of the rules, rule number 2, say the analysis starts from where? This is the analysis direction. Yes or no? Right? That is our analysis direction. And if we were to look at the area to be considered, right? There's a rules that say what? The first moment of area cannot cross the what? Centroid. Yes or no? Right? So the area to consider is this area for beta. All the 5 rules that I state still works. Okay? All the 5 rules. Okay? Okay, now I know it's very good morning early, okay? We will do some examples, okay, on how to sketch the shear flow. Okay, we will do some examples.